Linux Kernel 6.19 just got officially released by Linus Torvalds, so we're going to move on and see what's going to be staged in 6.20. Well, it's not going to be 6.20. Instead, Linus has officially announced that the next kernel is going to be called kernel version 7.0. Today, we're going to be checking out some of the exciting staged updates. Let's get right into things by first talking about a patch that has officially laid the claim that the Linux kernel has finally concluded the Rust experiment. That's right, with the Linux 7.0 merge window now open, kernel developers are officially declaring that the Rust for Linux experiment is complete and successful, marking it down as a permanent part of the kernel and signaling long-term commitment and continued investment from developers of the Linux kernel. This is big news. This officially means that the kernel is expanding its core language toolbox with C and Rust, as Rust has seemingly earned its seat at the table for the next decade of development. And with something getting added to the kernel, there is also something being taken away here. Linux is officially saying goodbye to the high PPI driver. For those of you unaware, this was the near gigabit networking standard that helped power some of the late 80s and 90s supercomputers, and it has officially been slated for removal in Linux kernel 7.0. The change will nearly drop 3,000 lines of long unused and unmaintained code, marking the end of this legacy technology that's actually been obsolete for decades as modern networking races into the terabit speeds. It's always nice to see a little bit of cleanup getting staged up, and it's just wild to see how much old code really exists in the kernel even to this day. Now let's talk a little about CPUs and scheduling, as Linux 7.0 is set to enable Intel TSX default on supported non-vulnerable CPUs, switching the default mode from off to auto. So what does that mean? That means Linux will automatically use CPU speed boost features when it's safe to do so. What is TSX? TSX is a CPU feature that helps threads work together more efficiently by reducing the time they spend waiting on locks. And before this, Linux kept TSX turned off by default for everyone, even with newer Intel CPUs, because of old security bugs from years ago. This is awesome, as many people with Intel TSX are going to benefit, especially ones using things like virtualization or that have highly multi-threaded applications. Some of us are going to start seeing a small but noticeable performance gain thanks to this faster locking feature. And in another stage change, we're talking scheduler changes for CPUs as the plan here is to further restrict the preemption modes. Basically, we're restricting modes on many different architectures, including x86, ARM64, RISC-V, and more, to just two different preemption models, which are the full and lazy preemption models. What is preemption? Preemption is how Linux decides when it's allowed to interrupt a running task in the CPU. So another task could run, and that is called preemption. And the two ways now are full preemption, which allows you to interrupt almost any time. So that's the best responsiveness. And then lazy preemption is allowing interruption at safe, sensible points, which just gives you good balance. And why just limit it to these two? Well, older preemption models, including no preemption and voluntary preemption, have been really kicked out because modern kernels expect preemption to exist. So having something like no preemption doesn't really make any sense. And then voluntary preemption only yields when code remembers to use it or do it. And it just relied on too many manual function calls, like a condition to reschedule manually, which made things very hard to maintain. Anyways, this simplifies the kernel code, reduces scheduler bugs, and improves consistency across distributions. A great thing coming to Linux 7.0. And now let's move on to talking a little bit about memory management and caching with resource management as a part of staging with revocable resource management. With this stage patch, a new safety feature will be given to us, which will help prevent crashes and security bugs when hardware is unplugged or removed. The change lets drivers safely detect when a resource, like a USB device, is gone and fail cleanly instead of accidentally accessing freed memory, making the kernel more robust, especially for Hotplug devices. And you might be asking, how will this work? Well, before, this part of the Linux kernel could still be holding onto a pointer something that no longer exists. And if code ever tried to access this pointer after it had been assumingly freed, well, that would cause crashes, corruption, or even a security hole known as a use after free bug. This new Linux system here is just going to go through these pointers and double check if they even exist. So think of it as, before I use this pointer, let me double check if it's real. If it is real, great. If it's gone, Linux backs away safely instead of crashing or allowing a vulnerability to take place. This is definitely a pretty cool way of handling things. And if you think these types of things are pretty cool, make sure to subscribe below and smash that like button for more videos just like this. Let's talk about another cool and potentially small performance boost from expanding the use of something called Sheaves, a new per CPU memory caching system, as it was initially introduced as opt-in, but the goal was to eventually move all caches to them. And this is the next step that's being taken in Linux 7.0, which will enable Sheaves for all caches, except in very special cases. This makes Linux's core memory allocator and work for more modern devices going forward. For those of you unaware, Sheaves are just a newer, simpler structure for Linux to keep track of small chunks of memory or cache for fast reuse on CPUs. The kernel has to constantly do things like allocating these small objects, freeing them, and reallocating them very soon again. And doing that directly from global memory would be slow, so Linux, of course, uses these caches, and historically used per CPU partial slabs. Sheaves are just a modern replacement for this idea. So before, each CPU had partially used slabs of memory, and each slab tracked things like free lists, counters, numerals, and locking edge cases. This hurt us because it required extremely complex code. It was hard to reason out, which made it fast but fragile. The new idea here, instead of caching whole partially used slabs, each CPU keeps a very small array of recently freed objects, which means you don't have to bookkeep slabs and didn't have to juggle around partial slabs. Sheaves simplify everything by managing just objects and helps remove slab state machines, partial slab lists, and slab freezing or unfreezing logic. And the takeaway here is that Sheaves is just going to replace some fragile code into a simpler structure for per CPU object caches. This cuts out complexity, deletes tons of code, and improves performance by reusing hot memory more efficiently. It's pretty cool stuff. Definitely check this out if you're interested. I'll put a link in the description below. Lots of great things coming to Linux kernel version 7.0. We're also getting OpenTree namespaces to provide a boost in performance and security, as a new option for the OpenTree system call will help create containers faster and in a safer way. How does this work? Well, it avoids copying and destroying unnecessary mount trees when launching containers. This can cut overhead and reduce system call turn. This can also deliver up to 40% faster container creation, and of course comes with added security benefits because it uses mount isolation. All pretty cool news, as traditionally when a container starts, Linux usually clones the entire mount namespace and then copies all the existing mounts, builds a new root file system, pivots that root, and recursively unmounts the old tree. That creates a lot of copying, system calls, and locking with massive overhead. With this new proposal here with OpenTree namespaces, Linux now just copies only what you need and starts clean. You call OpenTree, which creates a new mount namespace, copies only the specified directory tree, and mounts it in root inside of that namespace. No full mount table copies, which reduce overhead a lot. That gives us only one mount tree, no teardowns, fewer system calls, and less of that locking. And in some claims, with real-world testing, with the older pivot root based method, I could create about 73,000 containers in 60 seconds. With the newer OpenTree method, I can create about 109,000 in the same time. So it's likely that the new method is roughly around 40% faster than the older scheme, again with a lot less system calls. So who benefits from stuff like this? Well, it's really containers like Kubernetes, Docker, Podman, managed container services, Containerd, and many more platforms. Cool to see this type of thing. It's always cool to see these types of optimizations. And if you're ready to level up and optimize your Linux experience today, check out my checklist, cheat sheet, and mind map, all available at SavvyNik.com. Get your sheets today. As the next thing I want to talk about is context analysis as a language extension, which is set to enable statically checking by acquiring and releasing user-definable context locks. What does this mean? Well, we're set to gain a compiler-based context and locking analysis, which is a feature that can help kernel developers spot broken locking rules and unsafe code paths even earlier. This helps reduce bugs, race conditions, and hard-to-debug crashes. And to oversimplify things, the compiler will now understand how kernel locking rules actually work. With this patch, developers can teach the compiler rules like this variable is safe versus not safe if the lock is held, or something like this function may not be called while holding this lock. That means that the compiler can now check those rules while building the kernel, and if the rules get broken, you can get warnings before even booting the kernel. Also to mention, this feature requires Clang 22, which is currently unreleased, as it has smarter static analysis and ability to track these complex context locks. And this patch will plug those capabilities directly into the kernel and allow developers to use compiler catch locking and find context bugs well before the kernel crashes from one. Very cool stuff for devs and maintainers using Clang 22 with Linux Kernel 7.0. Speaking more on tooling and compiler optimizations, let's talk about this patch, which is lining up better performance for Rust-enabled LTO-built kernels. LTO just means link time optimization, and with LTO enabled, the kernel gets a full whole program view at link time, and it can see across all functions, across all files, and enables the Linux kernel to do fewer function calls with faster execution, have smaller binaries with better cache usage, and better cross-language optimization, especially when you're working with C and Rust. This means kernel developers will benefit when writing Rust code, and then users or Linux users indirectly get faster system calls and lower CPU overhead. So this change here will improve optimization when using LLVM or Clang with the link time optimization, making Mix-C and Rust kernel code faster and more efficient without actually changing any behavior. But there is some downside here, as LTO is known for making builds slower, as the compiler has to analyze the entire kernel space at once and can use more CPU and RAM. It's also harder to debug, as LTO can aggressively rewrite code as functions get inlined, code gets reordered and removed, and stack traces become a little less intuitive. Of course, there are some limitations as well. So there are definitely trade-offs. With faster runtime means slower builds. With smaller binaries, we get more RAM usage. And while we get help combining Rust and C and talking between the two, we get toolchain complexity with harder debugging. Anyways, LTO is great for production and large deployments, but not necessarily great for when you're initially developing and debugging. Cool to see this patch ahead of Linux Kernel 7.0. And now I'm ready to move on to some graphics drivers and some GPU patches ahead of Linux 7.0, as we're getting early AMD GPU updates, which are enabling a wave of new graphics and compute hardware blocks in the kernel. Most notably here, we're getting GFX 12.1 and RDNA 3.5 components. These updates come via the AMD GPU and AMD KFD drivers, preparing Linux for upcoming Radeon GPUs, improving the ROCm compute support, and bringing fixes, including performance improvements across graphics, displays, and memory management when it comes to GPUs. Well ahead of newer official hardware launches, big win for staging up the next generation changes for AMD GPUs. Ton of other things getting added and supported. Always great to see these types of fixes, improvements, and updates, especially when it comes to components, and as AMD tends to really lead the charge when it comes to graphics on Linux. And as the staging and merge window opens up for Linux Kernel 7.0, we're getting much more detailed temperature reporting on Intel GPUs. This is brand new with the Intel Xe graphics driver. It will officially expose multiple new thermal sensors throughout the standard hardware monitor interface, and users with monitoring tools will now be able to see the GPU's temperature limits, memory controller temperatures, PCIe temperatures, and even per VRAM channel temperatures. This makes it much easier to monitor the internals and thermals of Intel GPUs. We can also use this to tune things like cooling and diagnose issues on modern Intel graphics as we get upcoming new graphics cards with Battlemage, Panther Lake, and Nova Lake platforms. One note here is this pull request brings a revert of a flag in the new multi-queue UAPI that had been added in the first pull request of this round. After that pull request with multiple UAPI changes, I scrutinized them and found out that this flag was not used nor planned to be used, hence I requested removal before the 7.0 deadline. So we're definitely looking to make sure that we keep things not only updated but balanced as we go back and check our changes. Very cool stuff to see from Intel and for Intel GPUs. And another win for Intel's Xe graphics driver, they're set to add multi-device shared virtual memory support and smarter SRIOV scheduler groups. These changes will let multiple Intel GPUs share memory more efficiently for AI and compute workloads while improving GPU virtualization by better dividing hardware resources across virtual functions. The result will hopefully lead to better performance and stronger support for multi-GPU setups like the Intel Arc Pro and the upcoming AI accelerator platforms just in time for Linux 7 and Ubuntu 26.04 long-term support. So overall, this allows GPUs to work together. There's less wasted memory and helps Linux catch up to serious data center GPU features, especially when it comes to using Intel's newer Pro graphics cards. An interesting tale here in a blog post ahead of Linux 7.0, as a tale comes from Nouveau called A Tale of Two Bugs from Dave Erlai, in which he expects to restore and fix large memory page support in the Nouveau NVIDIA driver, hopefully unlocking better performance for the Mesa NVK Vulkan driver. The bugs previously forced features to be disabled despite promising speedups and now have been fixed, especially when it comes to things like memory compression and large pages. And basically, once merged, we're going to see noticeable gaming and Vulkan performance gains for users running the open source Nouveau stack instead of NVIDIA's proprietary driver. A big win for the Nouveau stack, and especially those users wanting choice between open source and proprietary drivers. And this here is the recommit of that compression support with Nouveau 1.4.2 or newer. This, along with the kernel side fix, will allow large pages and compression to become safe again. Let's talk about device trees and firmware a little bit, as we see an update from Apple System on Chip DT for the 6.20 kernel release. Well, 6.20 became 7.0. And what does it do? It's going to add specific functions for fully wiring up USB-C ports on Apple Silicon Macs by adding all the missing device tree pieces needed now for proper USB 2.0 and 3 support, including Type-C support. These updates describe how Apple's USB-C hardware blocks are connected and allow Linux to correctly expose and use every port on Apple M1 and M2 systems. The result is awesome, as it is a step towards complete reliable USB-C functionality on Apple Silicon under Linux. Very cool to see, and a lot of Apple users are going to be very happy with this staged merge and patch for Linux 7.0. And with this device tree support being added in, we also see another patch that supports it as we enable the drivers for Apple Silicon by default now, instead of requiring users to manually enable them, which makes Linux boot and work right out of the box instead of having to do manual intervention on Apple Macs, all after figuring out those device trees and updating them. From the other side of things, Microsoft's DSM function 9 to turn on a display has support being added into Linux kernel 7.0, as this ACPI signal is a crucial firmware notification used by modern Windows laptops as a signal to wake up from sleep, and without it, Linux could leave hardware in a broken state. Basically, think fans not spinning or keyboard and backlights just staying off when not calling this method during resume. Linux fixes this real suspend resume bug, which has already been confirmed on a few Lenovo Yoga models, and will help improve reliability on modern standby Microsoft devices and laptops going forward. The patch defines a new function index and invokes it with this execution order: LPS 0 exit function 6, turn on display intent function 9, modern standby exit function 8, and screen on function 4. Before, we could get stuck in a sleep state without ensuring that everything came up before actually turning our screen on. Anyways, a bit of a mess getting fixed. For those of you who are Framework laptop users, specifically the Framework 13 laptop, we're going to be seeing smarter fan control and temperature limits. By extending the Chrome OS embedded controller driver, Linux will now be able to set fan target speeds and respect temperature warning critical thresholds while using hardware monitor controls. The result will hopefully lead to better cooling behavior and quieter thermals, all with more predictable fan operation right out of the box with the Framework 13 laptops. A big win for Framework as we hit the staging for Linux kernel 7.0. Let's talk a little bit about networking. With Linux 7.0, we're getting CakeMQ, which is a new multi-core friendly version of the popular Cake network scheduler. And instead of bottlenecking traffic shaping on one CPU core, CakeMQ can spread across and work with multiple CPU cores while all still enforcing one global bandwidth limit. This makes traffic shaping scale properly on today's high-speed multi-queue network card, especially benefiting things like Linux servers and data centers where they need high-end routing and very, very fast links. So the old Cake, there's only one CPU per core, which would create traffic jams at very high speeds, and the new CakeMQ will allow for multiple CPU cores, and we can now move in through parallel, but we all are going to respect the same speed limit still as we spread the work across multiple CPU cores. Of course, this will help bandwidth. And now let's talk about a bit of a win for some creators using the Focusrite Forte, as we're officially getting support for this USB audio interface, meaning that this compact recording device will finally work out of the box on Linux, even though it's been discontinued. Users already owning one of these Focusrite Fortes will get full mainline kernel support thanks to community patches landing in the sound subsystem. And this is something that the Linux audio community has wanted for a while, as some Focusrite devices have not officially been supported on Linux, even though users have been asking for it for many years. And now Linux users will get proper kernel support for some of these Focusrite audio hardware drivers. And finally, I'm going to end it on here, as we're going to make it a lot easier to customize the boot logo instead of manually patching the kernel source code and files to replace the TUX Penguin. Users are now able to select a custom boot logo directly through kernel configuration options, supporting things like monochrome, 16-bit color, and 224 color images. This brings in cleaner customization for things like distros, vendors, and people who just want to tinker around with the Linux kernel. Pretty cool to see, as the kernel build process now has a category for logo. The string entry can take a path to a PBM or PPM image, allowing the user to more easily provide a custom logo without having to modify the source. They give some example, as you can update the make file accordingly. When converting to a C file, the logo will have one of these fixed file names, and of course it's dependent on what you're using, the monochrome, 16-bit color, or the 224 colors. And then depending on that image type, regardless of the name, the PGM or PPM source file name will allow for further simplifications in an upcoming change. And in this project, you can see with the Amadeus project how things look with their own modified logo in the boot process. Very cool to see. Always exciting to see all these Linux kernel updates getting staged as we head into Linux kernel 7.0. It's officially named 7.0. All exciting stuff. What are you mostly excited about? Is there something that was missed? Post it in the comment section below. I'd love to hear from you. Catch me in a great community on Discord, and I'll catch you in another kernel version. Thanks for watching.